First, I'd like to thank the organizers for the invitation. So now please imagine yourself change from the Pacific Ocean to the Atlantic Ocean, which is closer to us. So I give a brief introduction to the mid-ocean ridge. We know it's divergent plate boundary where two plates move apart, and it's also constructive plate boundary. And this figure here shows the distribution of the global mid-ocean ridge. And the global ridges has been classified into 4 types based on their spreading rate, from fast spreading to ultra slow spreading. And along the spreading ridge, the two plates move apart from each other, and then the mantle upwells. It undergoes decompression melting, produce the basaltic melt, and then the melt will migrate upwards and finally accumulate in the magma reservoir in the crust. And here, the figure on the right-hand side shows the crustal accretion model in perspective across the ridge direction. So the melt accumulates in the axial magma chamber, and a portion of the melt will erupt to form the upper crust, and then the rest will cool and crystallize to form the lower crust. So as Milena has introduced, so they tried to explore or image whether melt present in the crust. So here is an example from the fast spreading ridge, the same study area as Milena. So the figure on the bottom shows the reflectors, and which can interpret the seafloor reflector, the layer 2A, 2B reflector, and the axial melt length reflector. And here I want to highlight the axial melt length reflector at fast spreading ridge is almost continuous along the ridge axis, and at about 1 to 2 kilometer depth below seafloor. If we have a look of the crustal structure formed at fast spreading ridge, the same study area, and here the figure on the right-hand side is the tomography model, and we can say the crust shows a 2-layer structure with smaller velocity in the upper crust. But here, the figure on the bottom are some 1D profiles extracted from the tomography model. And the upper crust has small velocity, but high velocity gradient. And the lower crust has higher velocity, but significantly reduced gradient. And in the tomography model, this white line indicates the mohole the mohole, and we can say the crust has a very small variation in thickness along the ridge axis. And this suggests relative uniform melt supply along the ridge. So this leads to the development of this model. So at fast spreading ridge, the melt is produced in the mantle and then propagates nearly vertically to the crust and finally stored in the lower crust. And then the melt will erupt to surface through nearly vertical dikes. And then finally form the lava flow on seafloor and dike underneath. But if we have a look of the slow spreading ridge, it's very different. First, the axial melt length in the crust is usually not imaged at slow spreading ridges. This indicates the axial melt length is a transient structure at slow spreading ridge. But at only 3 sites, we have observed the axial melt length beneath the Iceland, and on the Reykjanes ridge, and at the Lucky Strike ridge. So the first example here is the Reykjanes ridge in the North Atlantic Ocean, which is influenced by the Iceland hotspot. And at this ridge segment, the axial melt length is about 100 meter thick, 4 kilometer wide, at about 2.5 kilometer depth. And its lateral or along ridge axis extension is not constrained. Another example is the Lucky Strike ridge segment at 39 degrees in the North Atlantic Ocean. This ridge segment is 70 kilometers long, and seismic reflection study has imaged the axial melt length, which is here. On this ridge segment, the axial melt length is about 7 kilometers long, 4 kilometer wide, at 3 kilometer depth. And if you consider the whole ridge segment is 70 kilometers long, but the axial melt length is only 7 kilometers long, confined to the segment center, then we want to ask the question, so how the crust is formed on slow spring ridge like Lucky Strike? That's the purpose to conduct this research. So the Lucky Strike ridge segment, 70 kilometers long, locating about 400 kilometers south of the Azov. This segment, as shown in the bathymetry map, here is the Lucky Strike. This ridge segment is bounded by non-transform offset on both segment ends. It's characterized by a well-defined axial valley. The valley is about 15 to 20 kilometer wide. Here, this figure shows the seafloor variation along the ridge. It's shallowest at the segment center, about 1.6 kilometer, and then gradually deepens towards the segment ends. And off-axis, you can see here, the seafloor morphology is dominated by ridge-parallel abyssal hills. And the current spreading rate of this ridge segment is about 20 millimeters per year. If we blow up the central part of this ridge segment, we can say at the segment center, there's an axial volcano. The volcano is about 6 kilometers wide and 15 kilometers long. The earthquake swarm and continuous microseismicity indicates on this ridge segment, there's continuous dyke intrusion, but mainly vertical dyke intrusion. And on the volcano summit, there are several active hydrothermal vents, which is shown in this figure, the white triangles. So we had a seismic experiment in 2005, a seismoma experiment, and we collected two wide-angle seismic profiles, one along the ridge segment and another one perpendicular to the ridge axis. And today I will only focus on the one along the ridge segment, along the ridge axis. So 10 ocean bottom seismometers were deployed along this ridge segment at 4.5 to 12.5 kilometer spacing. And this seismic profile has been shot for 3 times using different shot spacing, either 450 meters or 150 meters. So here is an example of the data. And from this seismic section, we can see clear the PG arrival, which is the turning rays from the crust. And we can see at far offset the PN arrival, which is the turning rays from the mantle. And in between, we have a narrow PMP arrival, which is the reflection of the Moho discontinuity. So the approaches to process the data in my study is I performed travel time tomography to get a low resolution model, and then use seismic full waveform inversion to refine the velocity model. So here I show you the final result. The figure on the top is from travel time tomography, and on the bottom is from seismic full waveform inversion. And before interpret the velocity, I directly tell you, so the final inverted model has a vertical resolution of 750 meters and a horizontal resolution of 7.5 kilometers. And now let's first talk about whether do we have a crust-to-mantle boundary on this ridge segment. So on this ridge segment at 2 locations, we interpret the Moho transition zone, which is shown on the right in the figure B. So these 2 figures, the top one is velocity model, and the second one is vertical velocity gradient. And we can see there at 2 locations, we have high velocity gradient, and the 1D velocity profiles was shown on the left-hand side. And for the Moho transition zone A, the velocity increased from 6.8 kilometer to 7.6 kilometer. And at transition zone B, the velocity increased from 7.2 to 7.9 kilometers, typical from crustal velocity to mantle velocity. And the Moho transition zone for both the 2 transition zones, they are about 10 kilometer wide and 1 kilometer thick. But at other locations, we don't have this kind of structure. So to investigate the crustal thickness variation, we actually use 7.1 kilometer velocity counter as a proxy of the crust-mantle boundary. So as shown in the figure A, the magenta curve is the 7.1 kilometer per second velocity counter. And in figure C is the crustal thickness variation. And we can see the crust is thick at the segment center, 8.4 kilometers, and it gradually thins towards the segment end. And at the segment end, it's about 4 kilometer thick. And the average or the mean crustal thickness is 5.2 kilometers. And this large crustal thickness variation indicates strong melt focusing to the segment center. Now let's talk about the upper and lower crust. So in this research, we use 7.5 kilometer per second velocity counter to represent the boundary between upper and lower crust. And then we calculate the upper crustal thickness and lower crustal thickness. So in the figure C, this brown curve shows the upper crustal thickness variation. It has small variation. The average is 3 kilometers with a standard deviation of 300 meters. And the upper crust shows a high velocity gradient. And then the lower crust, which its thickness is shown as this in this black curve. It's thick at the segment center and then gradually thins towards the segment end. And we can see the crustal thickness variation mimics the lower crustal thickness variation. So this means the large variation in crustal thickness is accommodated by oceanic lower crust. And the lower crust is very thin at segment ends, only 500 to 700 meters thick. So to interpret this velocity structure, we first consider whether the low velocity in the upper crust, it's a real magmatic upper crust, or it's because of the exposure of mantle rocks, or is there any oceanic core complex? We know at slow spreading ridge, at the magma style portion of the ridge, the plate separation can be accommodated by low angle detachment faults, which can exhume the lower crustal gabbro or upper mantle to the seafloor and form this kind of smooth corrugated seafloor morphology, and which is called oceanic core complex. And the mantle, they interact with water to form the serpentinized mantle, and the serpentinized mantle can show similar velocity as crustal rocks, which is shown in this figure. This line shows the variation of serpentinized mantle velocity, and here is the range of crustal velocity. So first, I will say there are some dredging studies from this ridge segment, and the rock samples collected, which is shown in this figure, the diamond or white circles, are mainly basalts. And to my knowledge, there's only one piece of serpentinized peridotite was dredged from here, which is called the Menes Homme Massif. This red star. It's at the ridge non-transform intersection region, not within the ridge axis. So also for the seafloor morphology study, and the seafloor within the axial valley is dominated by axial volcano ridge, and there's no clear evidence for the corrugated surface morphology. So this suggests there's no huge amount of serpentinized mantle at crustal depths. And also there's a seismic reflection image. In this study, they image the boundary between layer 2A and layer 2B. And so here, in this figure, this reflector is interpreted as the layer 2A 2B boundary. And these two figures are the same, but the bottom panel just remove the seafloor effect. And here you can say the layer 2A is constantly thick for the central 40 kilometer of the segment, and further towards the segment end, the layer 2A becomes thinner, and the layer 2A 2B boundary becomes distorted. They also find layer 2A 2B boundary is subparallel to the 4.5 kilometer per second velocity counter. So they interpret this boundary as a lithologic boundary. So all these observations, overall, they suggest we do have a magmatic upper crust along the whole ridge segment. So now let's take all the observations together. We observe the axial melt length, 7 kilometers long and confined to the segment center, but the ridge is 30 kilometers long. And we know the oceanic upper crust is uniformly thick along the entire ridge segment, but the lower crust is almost absent at the segment ends, which means almost there's no melt accumulate and pose there. So based on all these observations, we propose for the slow spreading lucky strike ridge segment, the lateral dyking or melt is the primary mechanism for crustal accretion. And here, which is summarized in this sketch, so we have the magma chamber at the segment center. This direction is along axis direction to the segment end, and this direction is cross-axis direction, and the melt can lateral migrate from the magma reservoir at the segment center to the segment ends. And during this lateral dyking, there may be some facial eruption occurs to form the lava flow. And we don't have other geophysical observations to support our interpretation for this ridge segment, but we have some geochemical evidence. And in this study, they study the basalts dredged or collected from the Lucky Strike axial valley, and they found the basalts shows a systematically decrease in magnesium oxide away from the segment center. Here is segment center, and this is to the segment ends. And they interpret this as due to the cooling and fractionation of melt during the melt propagation, and which can be interpreted by two models. The first model, they only consider lateral dyking, where the melt produced the mantle is focused to the segment center and then redistributed towards segment end. In the second model, they include the melt propagation directly from the mantle to the crust at the segment ends, because there's no, in this study, they don't have strong evidence to exclude the vertical melt migration from the mantle to the crust. But in both models, they have to invoke the lateral dyking for crustal accretion. So here I summarize. So here I summarize. I conclude my presentation. So on the Lucky Strike ridge segment, the crust thins by 50% from the center to the ends, this indicates strong melt focusing to the segment center. And the large variation in crustal thickness is mainly accommodated by lower crust because the upper crust has very small variation. And we propose the upper crust on the Lucky Strike ridge is mainly formed by lateral dyking or melt, with the melt sourced from the magma reservoir at segment center. And we suggest this lateral dyking or melt should be included in numerical modeling of crustal accretion or other interpretations, at least for slow spreading ridges. Thank you.